Hi guys, welcome to the decision tree lecture. In this section, we will talk about decision tree learning and its type with some practical examples. Let's start with an example where I have a situation. My son wants to practice soccer. Before I decide to go out with him, I do have few questions on weather. I'm starting with the outlook and have three routes or splits from there: sunny, overcast, and rainy. If it is overcast, no more questions and we are playing. If it is sunny, then my next question is regarding wind. There are two further splits, options, or we can say routes at this point: yes or no. If the answer is false or no, we are playing outside. The third route is rainy, which raises another question regarding humidity and leads to play if the humidity is normal. Decision trees are used for both the classification and regression problems. In the example above, we notice that the sequential questions needs to be answered from top to the bottom along a certain route to find out the outcomes. This is like if-else condition, which ultimately yields a specific result at the end. Let's explore a little more on the tree and its main parts. In our decision tree example, outlook, which is in darker blue color, is a starting point. This starting point in a decision tree is called root node. Black lines are connecting nodes and also show the flow from question to the answer. They are branches. So the branches connect the nodes and typically have answer to the question that we ask at the node. At the end of the tree, there are terminal nodes represented in green color. They are also called leaf nodes and predict the outcomes. The trees could also have internal nodes. For example, windy and humidity, represented in lighter blue color. They split for the value of a certain feature, for example, true or false for windy and high and normal for humidity in our case. In decision trees, both the root and leaf nodes contain questions or a criteria to be answered along the route between them. Trees have their depth, which is important and represents how many questions are asked before we reach the leaf node or predict a class. The overall depth of a tree is represented by its longest root. In our example, the depth of the tree is 2 for both sunny and rainy roots. For the overcast root, the depth is 1. However, the tree has a depth of 2. Another thing we notice in the tree is splitting at the nodes. A relevant and most important question is how to decide a split, which is the best under given circumstances. So our concern is to find out the best split. Let's learn with a simple example where we have three features A, B, and C, and two target classes, green and blue. If we look at B, it has 1 for the green class and 0 for the blue class. As we see in the tree on the right side, splitting at B gives a clear separation between the green and blue classes. Let's go into little more details and create a table to see how this splitting is working. In the table at left, we see that for A equal to 0, we get only one blue target value. For A equal to 1, we have 2 green and 1 blue target value. So we got 2 classes for the same target value. Let's consider C now. we have one green and one blue for both c equal to 0 and c equal to 1. So splitting at c is not really helping us at all, because we are getting both classes for yes and no. B is our third option, which is giving two separate classes, green for b equal to 1 and blue for b equal to 0. Hence, B is the best split in this case. So the focus is to choose the feature that gives the best split, such as B in this case. If we split at B, we have the maximum information gain, and this is what we want from our split. This was a very simple example. There is mathematics involved behind the split. Let's have a look how the mathematics work behind a split. To understand this concept, we need to understand entropy and information gain. Let's talk about entropy first. Entropy is a common way to measure the level of impurity in a group, and it comes from the information theory. Remember, higher the entropy is, more the information contents are. Mathematically, entropy can be written as a sum of the product of the probability of I and its log 2 value, where I ranges from 1 to n. Now it comes to the information gain, which is based on entropy. Information gain decide the feature to split on at each step while building the decision tree. Information gain is equal to the entropy of the parent node minus the weighted sum of entropies of the children. Let's do some mathematics to see the splitting by calculating the entropy and information gain. Let's consider the same example where we have three features A, B, and C and two target classes green and blue. While splitting at A, if we calculate the entropy using the formula from the previous slides, the entropy for the parent is 1. Splitting results into two children, green, green, blue, and blue. For child 1, we calculate the entropy equals to 0.92, whereas the entropy is 0 for child 2. Using these values of entropy, we get the information gain equals to 0.31 for splitting at A. What if we split at B? We can calculate information gain in a similar fashion, and the value for information gain we get is equal to 1. The third option is splitting at C. Following the same steps, we have no information gain in this split. The value of information gain is 0. To summarize the values of information gain for splits at A, B, and C, let's create a table. From the table, we clearly see that the maximum information gain is when we split at B. So, splitting at B is the best option because we want to maximize the information gain while splitting. C gives the worst split, where A is somewhere in between, but still B is the best, which is chosen. This might be too much on mathematics. Don't worry. You don't need to do all these calculations by yourself. Your algorithm will do this automatically when you will work in Scikit-learn. However, it's good to know how the things work at the back end. So, now let's talk about the advantages and disadvantages of the decision trees. A decision tree is actually a kind of flow chart that yields various outcomes based on the series of decisions or questions. One of their primary advantages is that they are easy to follow and understand. Decision trees are fast and can handle both numerical and categorical data in the larger data sets. There are some disadvantages associated with the decision trees. Although the decision trees are computationally cheaper for predictions, however, they can be computationally expensive while training. In decision trees, utilizing different training and test subsets of the same dataset leads to have a high variance. Decision trees can be very easy to overfit. Overfitting is creating over-complex trees that do not generalize the data well. This results in poor performance on unseen data. This primary weakness limits their usage in predictive modeling. However, the positive side is that we can use ensemble methods and create a model that utilizes underlying decision trees as a foundation to produce excellent results. So, with this, I hope you got good understanding of decision trees. If you want to learn more, please explore the suggested readings. Coming up are very important concepts of bootstrap, bagging, and random forest. The bootstrap is widely applicable and extremely powerful statistical tool that can be used to quantify the uncertainty associated with a given estimator or statistical learning method. Let's consider we have a data set with 100 values and we want to estimate the mean of the sample. Simply, mean is equal to the sum of all the values divided by number of values. For such a small sample, we expect error in the mean. However, using bootstrap procedure, we can improve the estimate of our mean using the following steps. The first thing what we do, create many random subsets, say 500 or maybe more, of our data set with replacement. Replacement is selecting the same values multiple times. After that, we calculated mean of each subset. Lastly, what we do, we calculate the average of all of our collected means and use that as our estimate mean for the data. For example, we had 5 subsets which gave the mean values 2.5, 3.5, 5.5, 4.3, and 2.9. The estimated mean in this case will be 3.74. Bagging is an application of Bootstrap. Bagging is a general purpose procedure for reducing the high variance of machine learning algorithms, typically in decision trees. This simple and very powerful ensemble method combines the predictions from multiple machine learning algorithms together to make more accurate predictions than any individual model. Let's consider another example. We have a sample with 5,000 instances or values. We want to use decision tree algorithm. The bagging procedure will work as follows in this situation. First, it will create many random subsets, say 500, 1000, or even more of our dataset with replacement. After that, it trained the model on each subset. For the new dataset, it then calculate and output the average prediction from each model. For example, we had 5 bagged decision trees, making predictions for a class G, G, B, G, and B. The most requested or mode is G, and that will be the final prediction. So the decision trees are greedy. They choose the variable to split on using a greedy algorithm that minimizes the error. Even with bagging, the decision trees can have lots of structural similarities and in turn have high correlation in their predictions. Combining predictions from multiple models in ensembles works better. If the predictions from the submodel are uncorrelated or at least weakly correlated. This is where random forests comes in as an improvement over bagging decision trees. So let's talk about random forests now. Random forests is one of the most popular and very powerful machine learning algorithms, which corrects the habit of overfitting of decision trees to their training dataset. The essence of the method is to assemble multiple trees in randomly selected subsets at training time and outputting the class that is the mode of the classes or mean prediction of the individual tree. Suppose one of the feature in our dataset is very strong and it's predicting a certain class. With bagging, most of the trees will use that feature as their top split to minimize the error. Remember, they are greedy. This will result in ensemble of very similar and highly correlated trees. Averaging highly correlated quantities does not significantly reduce variance, and this is what we don't want. Random forests does the trick. By randomly leaving out candidate feature from each split, random forests decorrelate the trees and make them independent from each other, so that the averaging process can reduce the variance of the resulting model, and it has no effect by the features that are strong at predicting a certain class. So this decorrelation is very important in random forests. A new random sample of features is chosen for every single tree at every single split. The number of randomly selected features, say m, that can be searched at each split point is specified as a parameter to the algorithm. Typically, if p is the number of full set of features, for classification, a good default value for m is square root of p. Like if we have 25 features, m will be 5 for the classification problem. In case of regression, a good default for m is p divided by 3. So guys, this was all about decision tree learning and random forests. We have covered the theoretical background and key concepts that governs the decision tree learning and random forests. Let's move on and work with data using Python machine learning library Scikit-learn. See you in the next lecture. Good luck.